All right, welcome back from the break, everyone. So we have another set of three speakers for this session. We'll start off with Guttorm Opshaug, who is an alumni of this lab. He holds a PhD and a Master of Science degree from the Department of Aeronautics and Astronautics from Stanford University. His PhD is from the GPS lab. And he has a BSEE from the Norwegian University of Science and Technology. After he graduated, Guttorm joined Jim Spilker's company, Rossum, which focused on terrestrial positioning using television signals. After joining Qualcomm, Guttorm has continued working in the same general field, and he's here today to talk about positioning with 5G, fifth generation cellular networks. So thank you, Guttorm, for talking about this hot topic.
Yeah, thank you for the introduction, Sherman. So I'm going to launch right into it too. And in the talk today, I'm going to kind of go through the standardization process in 3GPP, and I'll touch on some of the elements that I should go into that. And I'll wrap it up with a video from some of our field testing earlier in the year. So just with no further ado, so we have 3GPP, or the third generation partnership project, which is really the preeminent standardization organization for cellular communication and positioning. Now, you can probably infer something about the relative priority of those two by my carefully chosen font sizes here. But back when 3GPP was founded by these kind of 7 founding members, back in the late 90s, I think they wanted to be the be-all and end-all of all communication standards. Not only did they call themselves the third generation partnership project, and I'm here today to talk about 5G, but they also called their first standard the Universal Mobile Telephone Standard, or UMTS. Now, about a decade later, they realized things had probably changed too much. They couldn't really call things 3G anymore, and they wanted a new standard. And they probably scratched their heads a little bit, and they realized that, well, maybe even the universe can evolve, so they wound up calling it the long-term evolution, or LTE. Now, long-term is also a fairly relative term here, and again, 10 years later, there's now 5G. The first release was back in 2018, and I think at that point they just threw their arms up and just punted the naming and called it New Radio, or NR. Now, the way 3GPP is organized is kind of shown on this chart on the right-hand side here. There's kind of 3 main pillars here. There's kind of a services and systems group. Think of it almost as an application layer in like an OSI model. The central group here is the core network and terminals. That's kind of the internet and the cloud. And then on the left-hand side, we have the radio access network group, or RAN. So that's that has to do with anything that actually has an RF radio in it, being that a cell phone. I'll probably refer to that as a UE, or a user equipment. That's kind of 3GPP speak for any kind of device, or it could be a base station, of course in 5G called a G node B. But I'll focus most of my talk kind of in the upper left corner of this, kind of on the radio layer. So what exactly does 3GPP do? Well, they sure have a lot of meetings. Now, you may not think that having 5 or 6 meetings every year is too bad if you have 5 or 6 meetings every day. But these 5 or 6 meetings per year actually tend to last about a week or two. So they do actually carry a lot of workload there. And then the meetings are really there to drive the whole process forward, because there's typically like an update or a revision to the standard every 2 years. And at the onset of this whole process, you usually start with some use cases and performance targets. And that usually comes from that kind of services group. Now, 3GPP might provide you with some simulation assumptions. This could be channel models, or it could be kind of topologies. And then that enables different companies to, run their simulations and see if it's feasible to meet those use cases and performance targets. Now, out of all of this, you get several kind of deliverables. One might be a signal definition of signals that are useful for positioning. There might be measurement methods. And then you'll also have a lot of these protocols and call flows to tell you like which information elements are kind of needed, and what is the sequence that some of these elements might be exchanged with different elements. And last but not least, you actually have a group that generate these conformance tests. So an OEM can now go out and run these tests and actually validate that they do in fact meet the standard. Next, I wanted to zoom in on 5G positioning as it pertains to this most recent release 16 in 3GPP. So for release 16, there are two different types of use cases, a regulatory one and a commercial one. Now, the regulatory one is essentially E911. Commercial one is any type of kind of LBS application. And one thing to note here is that the commercial use cases are actually much tighter in terms of accuracy targets than the regulatory one. So the commercial one was brand new in release 16. There's never really been a use case like that before. And actually something else that's also brand new in release 16 is this UE-based method. So there are two types of ways to kind of treat positioning as far as the standard goes. There's UE-assisted, in which case a device may make some measurements, but the measurements are actually sent off to a server, and it's the server that calculates the position. UE-based, it's kind of the other way around. The device may make the measurements themselves and also calculate the position. So it really kind of goes by where the position is being calculated. Now, UE-assisted might make a lot of sense for E911, which is a case where hopefully none of us really need to use that very often. But if you dial 911 here in the US, first responders will be told your location and they can come find you. So hopefully that's something that is really rarely used, but most of the time, probably most of us really want to use our cell phones to go from point A to point B and find a restaurant or something. And in that case, it's really more valuable to have that location and position information like on your device itself. Another thing that's typically really important for positioning systems is the synchronization of the transmitters. And on the bottom left side here, I've actually kind of noted what the requirements or maybe a lack thereof are for the purpose of communication. So there are two modes of operation of these communication networks. It's TDD and FDD. TDD, since you're sharing the same frequency, you have to have some timing accuracy requirements. FDD, you don't really strictly have any. And one thing to note again is that for the purpose of positioning, if you want to have these positioning features, there are actually no requirements in 3GPP at all. Even though if you can look on the right-hand side and things I've kind of bold-faced a little bit and highlighted in blue, there are actually two of these measurement methods that really do require a very accurate synchronization of your network, because network synchronization directly impacts your end-to-end position accuracy. So here I've been fairly lenient, and I've said that, well, you could actually blow your entire error budget on just one error source, but you should probably at least keep that error source less than the end-to-end budget a little bit. Another interesting thing to note, though, and this actually kind of ties back to what we've talked about earlier in the day about resilience. There are actually some of these measurement methods that are fairly resilient to network synchronization. And next, I'll actually walk through all these 6 different methods here. So I've split them into 3 different groups. This first group I called pseudo-range-based methods. Actually, I'm going to just view my bar up there. In the sense that they work effectively by making pseudo-range type measurements. On the left-hand side, there's this downlink time difference of arrival method, where you have these transmission points that transmit some signal. You receive them, kind of figures out exactly when they were received. You might mechanize it as a TDOA type solution and get these hyperbolas, and at the intersection, you'll find user location. So on the bottom corner here, I kind of wanted to translate this to people that are maybe more familiar with GNSS and aviation. So this is pretty similar to GPS, or actually even more so to LoRaN. Now, on the right-hand side, there's actually an inverse method, in which case a UE transmits a signal, and now these reception points receive them. The navigation equations are actually identical, so you can still find the UE location. And the closest analogy I could find was the GPS kind of NUDET segment. All right, so moving on to the next set of measurement methods that use both uplink and downlink. On the left-hand side, we have this enhanced cell identity method that really works by using a metric called timing advance that's really used in the time tracking loop that runs on all UEs to make sure that the time of arrival of any signal sent from any UE to their serving cell arrives at about the same point in time. But it turns out that this TA metric is actually an estimate of twice the distance or the round trip time between the TRP and the UE. So you can actually get a distance measurement out of it. On top of that, if you know the location of your cell and the orientation of the antenna, and maybe even better, like the orientation of a particular beam from an antenna, now you have an angle and you have a distance and you can find your location. So I've kind of equated this to a VOR plus DME type solution. Now we've kind of taken this a little step further on the right-hand side using this multi-cell round-trip time method, where now we can actually make round-trip time measurements not just to the serving cell, but to a number of neighbor cells as well. So all in all, this kind of looks like a DME plus DME type solution. You get these circles, and at the intersection of the circles, you can find the U location. And lastly, we have a set of angle-based methods. Again, this is something that's completely new in release 16. So we have this uplink angle of arrival method. In this case, it's again the UE that transmits some signal. The reception points using their MIMO antennas can probably make some phase measurements and find the angle of arrival of that signal. If you have two or more of them, you can quite literally triangulate and find the UE location that way. So this is, again, pretty similar to kind of a direction finding method. And then lastly, we have the downlink version, or downlink angle of departure. Now, these MIMO antennas, or sometimes massive MIMO antennas, will actually do a sweep of different beams. They'll transmit some signal, and they'll do it kind of in different spatial environments. A UE will make measurements of all those different beams, figure out which one is the best, and then at the intersection of the best beams, you can find the UE location again. So pretty similar to a VOR plus VOR type solution. Now I'm going to switch gears a little bit and talk about frequency ranges, because that's also something that is a little bit new in NR or 5G. So there are two frequency ranges called FR1 and FR2, FR1 being the sub-6 gigahertz range, which now, of course, goes well beyond 7 gigahertz, but probably for historical reasons, it was called sub-6. And then FR2 being kind of the new kid on the block for 5G, being millimeter wave. So that's from the 20s of gigahertz up to the 50s of gigahertz. Now, if you kind of think about GPS and GNSS, you have three different frequencies, maybe L1, L2, L5. There's been a lot of discussion recently about like L5 versus multiple frequencies. I'm not even going to touch that without 10-foot stick here, but I'm just going to kind of make a comment here that for the purpose of 5G positioning, it's a bit of a moot point. Because there's actually 56 different band classes defined in FR1 alone. In FR2, you have 6 band classes. Now, a handset may not necessarily support all 56 band classes or anything, but they're very likely to support a dozen or maybe more. And even inside of each of these band classes, you can actually have separate kind of sub frequencies. So you'll definitely have a device that already comes with a lot of built-in capabilities. Now, moving on to the picture on the right, and pay no attention to the Blue Angels flying over San Francisco Fleet Week here. Actually, what I wanted to highlight is in the bottom right corner here. And I'm not 100% sure about this. And if someone else, knows better, please, speak up. But I do believe I've actually spotted both an FR1 and an FR2 antenna here. So you might notice this light post. There's this long cylinder here. It seems to be about this right size and shape for an FR1 type antenna. There's this hexagonal structure at the bottom of it. It really reminds me of the Opal and Sapphire satellites we built at SSDL. But those panels to the side there, they remind me also a lot about what some of these massive MIMO phased array antennas might look like. So by the way, I kind of jumped from that slide at the end. I actually have a pop quiz. I want to ask everyone how many planes you saw in that prior picture. But I'm going to move on to signals for now and just give a pretty quick kind of primer on OFDM, because these are the types of signals that are used in 5G and actually in 4G before that as well. And these signals are built completely differently from CDMA or Bach type signals that are common in GNSS, in the fact that they have these atomic building blocks called resource elements, and those are those little squares inside that kind of bigger grid. Now inside each of these squares, there's a subcarrier, and that subcarrier is transmitted for one symbol or for some period of time. So the x-axis here are number of symbols or time, and the y-axis are frequency. Now, one of these REs, again, you can really think of as maybe like a sine wave, and the sine wave has some amplitude and it has some phase, and it started at some point in time and it stopped at some other point in time, and that's kind of it. But then in the next symbol, you can have a different subcarrier being transmitted. And once you have these, kind of atomic building blocks, you can build what's called a resource block. That's this kind of rectangular grid here with 14 symbols by 12 subcarriers. And the way you can really enhance bandwidth in your system is you can start stacking these blocks on top of each other. And for NR, you can stack up to, I think, about 272 or 273 of these blocks. So that's, again, a way for you to kind of increase your bandwidth, increase throughput. There's actually another way to also increase bandwidth and throughput, and that's by changing the spacing between these subcarriers. And there are 3 options for that in FR1 and a couple in FR2. I also want to note that there's actually this inverse relation between that subcarrier spacing and the length of a symbol. On the bottom, I've kind of noted these intersymbol interference and intercarrier interference issues. They're all kind of taken care of by different means. I'm not going to spend time on that. But I want to show you the signals that are actually defined in 3GPP in release 16 for the purpose of positioning. So on the left-hand side here, we have the different signal structures of the downlink positioning reference signal. You can see there are 9 of them, and on the right-hand side, there's an equivalent, actually 10 options for this uplink sounding reference signal for positioning. By the way, not to be confused by with the uplink sounding reference signal itself. Those are 2 different things. Now, the way you kind of construct these signals, they're really kind of 2 parameters are important. One is called the comb size, meaning like how many subcarriers between each subcarrier that is actually used for a given symbol, and then the number of symbols that are used. So in the top left corner here, there's a comb 2 symbol kind of variant. Bottom right corner for PRS, there's a comb 12 symbol variant. I also want to provide a bit of kind of historical background because NR didn't really start by itself. It really did learn something from what came before it in LTE. And even in LTE, there was positioning reference signal, again, not to be confused with the downlink positioning reference signal, which is the NR version. And on the left-hand side here, I'm showing like one example of this signal. And a couple of kind of curious things you can notice that not every symbol is actually used. So symbol like 4, 7, and 11 are actually not used at all. In NR, all the symbols are contiguous. They're in use. Again, on the left-hand side, you can actually see that there are some symbols, or some carriers that are repeated multiple times. But then there's actually some that are not used at all. So there are these repeated holes in that frequency spectrum. That's again another thing that we kind of tightened up in NR and made sure that we kind of filled up all those holes and made a contiguous kind of frequency spectrum. If you were to kind of do your coherent integration across all these symbols. The last thing I wanted to mention here was we've kind of talked about OFDM and actually the way you would have different signals not collide with each other. You can shift all of these signal structures up and down, and in these cases there are actually 6 different options for that. You can shift everything up by 1, 2, 3, 4, or 5. And that's something that's actually really crucial for terrestrial positioning systems because you really have this near-far effect that could really impact you. Again, going back to that slide 12 with those antennas, I actually got pretty close to those antennas. And if I simultaneously had to be able to detect a signal from a more distant antenna, it's really important that that close antenna don't overwhelm my front end and my measurements. So a little bit back to those repeated holes in the LTE spectrum. Like, what does that actually mean? So in this next slide, I've actually generated the correlation peak or the channel energy response for both the NR and the LTE signals. And the way those repeated holes manifest themselves are through these alias terms. There are actually 6 of them, and then you have kind of the main lobe in the middle. And those alias terms, I mean, they're pretty far out. They're more than 3 kilometers out. They're pretty far down. They're about 13 dB down. But they're still kind of nuisances, and it's something that might keep you up, at night to worry about. So for NR, we got rid of that, and now on the bottom kind of red graph, everything is pretty clean. You don't have to worry about those alias terms at all, and you have this kind of sync-shaped roll off on your correlation peak. Now, if you were to zoom in on just that main lobe of the correlation peak, I've used 20 megahertz bandwidth option as an example here, because that's actually how wide of a bandwidth was available in LTE. Now, for NR, you can actually increase that bandwidth, by several order of magnitude or so. Starting off with 20 megahertz here, which is, by the way, also pretty similar to what most bandwidths are for GNSS signals, or at least some of the wider band ones. But then in NR, maybe going from 100 100 RBs up to like 270 or so RBs. On top of that, maybe reducing your symbol duration or increasing your subcarrier spacing. So you can go from a 20 megahertz bandwidth up to 100 megahertz of bandwidth in FR1. And then if you go to FR2, you can actually go all the way up to 400 megahertz. So now that's like a factor of 20, compared to this. Now, if you actually go up to 400 megahertz, those correlation peaks become really narrow, again, by a factor of 20 or so. And if you kind of do the math, I think you come out with, the null to null width of that correlation peak at 400 megahertz would be about 5 feet or so. And that's about, how wide someone can reach. And I think one way to think of it is like you could actually quite literally hug that correlation peak. It's that small, and you can, resolve multipath accordingly. So with that, I actually want to hopefully end this talk on a bit of a high note and show this demo video that we did for some field testing. And here we didn't really constrain ourselves to using just one of these measurement methods. We actually combined two of them. And the two we combine are actually fairly orthogonal. Multicell RTT gives you a range. Uplink AOA actually gives you both azimuth and elevation. So now you have three independent measurements in three different directions. You can actually get a 3D position fix from just a single cell. That's what we did at the beginning of the year. And then, of course, we added more cells and improved things kind of at mid-year or so. Now, I've heard that the soundtrack on this is pretty loud, so I'll give people like a few seconds here to maybe turn down their sound a little bit. But I really enjoyed the soundtrack, so I'm gonna run it with the soundtrack on here. All right, and yeah, with that, I think I'll open up the floor for any questions.
Thanks, Guttorm.
Do you want to ask the questions?
Yeah, it looks like there's one already in the Q&A, which is what sort of propagation environments does 5G have? What type of multipath issues arrive to affect the positioning accuracy?
Maybe from some of those kind of simulation assumptions, there are actually some very complex propagation models with especially for FRT, there are these like clustered delay line models. So you have different clusters of a lot of different reflectors, and then you have maybe some spacing to another cluster, and they can come from different directions and things like that. In terms of maybe like more general, I think I don't have too much experience with millimeter wave, but my expectation is that those waves are blocked fairly easily. So it could be a case where if you see a signal and you have really wide bandwidth, it's going to be incredibly good, but then things might be blocked, and then you might not see it at all. And then of course going down in frequencies, in FR1, yeah, those signals tend to penetrate buildings better and give you better indoor coverage as well, as you could also kind of see from the demo video.
There's another question about accuracy in heavy rain.
Yeah, we actually did have some terrible weather that actually made us have to kind of stop testing. You may see that our test equipment was not really weatherproofed or anything like that. But yeah, we kind of got hit by monsoons and everything. I don't think we necessarily tested in very heavy rain. For our frequencies, 2.6 gigahertz, I don't think it would have mattered a whole lot. Maybe at FR2, there could be more of an impact from rain.
Another question about the time synchronization and the accuracy is, you said, I guess it's not as high as on GNSS, and is the clock difference, is that important or because of the round trip delay or the round trip measurement?
Yeah, for those round trip time measurements, the only thing you really care about being synchronized is you kind of want your positioning signals from those 5 GNOBs to more or less overlap, so you don't have to search a wide range for them, because these signals are pretty sporadic. They typically last about a millisecond or so, and they come around every 160 milliseconds. So these aren't continuous type signals. So it's really more of an indirect impact that synchronization kind of wanted. You want it there to a certain extent, but you don't. It's not really driving your accuracy. Now, group delay, that's a whole different story. Yeah, that's definitely something that impacts the accuracy of RTT, because yeah, you have to calibrate both sides of that equation. And actually, in 3GPP, there are some requirements for that. Although I will have to say, and you might laugh at this, but in 3GPP, there are things that are mandatory, there are things that are optional, and then there are some things that are conditionally mandatory. Like if you have one thing, then you definitely have to have this other thing. And I think there was some talk about having an optional mandatory requirement, which sounds a little ironically, but yeah, that's how the kind of politics works sometimes in those standardization bodies.
All right, there's quite a few other questions popping up in the Q&A, but I think in the interest of time, I'm going to move on to our next speaker.